The population P of deer in a small forest is modeled by this differential equation, that is dp by dt equals 1 over 10 p times 100 minus p. And assuming initially there are 80 deer in the forest, we wanted to describe the long-term behavior of the deer population. So we must choose one of the answer choices given over here. And so for that, we have to first determine the p from this differential equation. Here we are going to use the separation of variables method to solve for p first, and then plug in the initial value of p as 80 here, and solve for the integration constant c. And then we have to let t approaches infinity and determine the value of p when t approaches infinity. So we will do that now. I'm going to separate the variables here. So I'm going to divide both sides by this expression p times 100 minus p, and also multiply by dt on both sides. So we can rewrite this equation as since we are dividing by 1 over p times 100 minus p, this becomes 1 over p times 100 minus p, and this is multiplied with the dp. We also multiply both sides by dt, and so this equals, we will have 1 by 10 over here and then dt. And now we can see that we have separated the variables, that is all p and its derivatives on the left side, and all t and the dt on the right side. And this means we can now integrate to solve for p. So basically we do the integration on both sides. Now let's focus on integrating this expression. Uh, Observe that this is a rational function in P. So we must use partial fraction decomposition method to write this as a sum of partial fractions, and then we can integrate it. So I'm going to integrate this first. So first let's use the partial fraction decomposition method and rewrite this rational function as like this, that is a over p, and then b is another constant. This is over the next factor, that is 100 minus b. Now we have to solve for a and b from this equation. Let's multiply both sides by this expression. And so when we do that, on the left side we'll be left with 1, and on the right side we have to multiply this side also with p times of 100 minus p. Let's do that. And here when we multiply this with the p times 100 minus p, these two gets cancelled with this two, and that's why we got 1. Now we have to distribute this expression into the expression inside the brackets. So a over p times of p times 100 minus p, you see that this p will get cancelled with p, and we'll be left with a times 100 minus p. And then when we distribute this expression with this one, we'll see that 100 minus p will get cancelled, but p will remain. So we'll basically have p times of p. Now let's simplify and solve for a and b. I'm going to put some random values for p and determine a and b. Let's say if p equals 0, we get 1 equals a times of 100 minus 0 is 100. So this is a times of 100, plus this is 0. So b times 0 is 0. And so we have this equation 100a equals 1. Solving for a, we get a equals 1 over 100. Now let's put p equals 100. When we do that, we get 1 on the left side. When we put p equals 100 here, this will be 100 minus 100 is 0. So this term will get cancelled. And then here it will be b times of replace p by 100. It is 100. And so solving for b from this, we get b also equals 1 by 100. So here we have solved for a and b, and this means we can rewrite this integral on the left side using partial fractions. So basically we have the equation integral of 1 over p times of 100 minus p, and this equals the integral of a over p. A is 1 by 100, and this is over p, plus b over 100 minus p. But since b is 100, we can replace 1 over 100 divided by 100 minus p. So this is what we have on the left side of the different after we have separated the variables. And on the right side, we have integral of 1 over 10 dt. So let's also write down here, this is integral of 1 over 10 dt. And we are now focusing only this equation. So these two sides we have integral. Now let's integrate both sides. I'm going to write down this as a sum of two integrals. That is, the first one will be this 1 by 100 is a constant which we can factor out of the integral, and then we have to integrate only 1 over p dt. And similarly for the second one, I can factor the 1 over 100 and then integrate only 1 over 100 minus p, and this is dp. This one is dp, not dt, since we integrate with respect to p. And on the right side, we can factor this 1 over 10, and then we have to integrate only dt or just 1 dt. Now let's integrate. So this will be 1 over 100. Integral of 1 over p is a natural logarithm of absolute value of p. And then this is 1 over 100. Integral of 1 over 100 minus p. This will be natural logarithm of 100 minus p. This is absolute value. But since we have a negative p, we should divide by the derivative of negative p, which is negative 1. So if we divide this by negative 1, this completely becomes so that means we can change this to negative, and this equals 1 over 10. Integral of 1 t dt is t. We also put the integration constant c. So we have integrated this. Now let's multiply both sides by 100 so that we can remove the fraction. So this side we multiply by 100, and also this side we multiply by 100. Let's distribute this. When we multiply by 100, these two hundreds will get cancelled, and so we will have only natural logarithm of p. And also when you distribute this 100 with this, we will have only natural logarithm of 100 minus p, this absolute value. And this equals, we'll multiply 100 with this one. So we will get 10 times t plus this will be 100 times c. Let's simplify this now and solve for the integration constant c using the initial conditions. Remember that we are told that initially there are 18 ATD, and this means when t equals 0, the population of t, that is p, equals 80. So we are going to place this condition to determine the integration constant c. So we must plug in t equals 0 and p equals 80 into this equation, and this means we will get natural logarithm of absolute value of 80 minus natural logarithm of 100 minus 80 is 20. So this is natural logarithm of absolute value of 20. And this equals, we plug in t equals 0. So therefore this will be 0 plus 100c. This basically is 100c. We can solve for c from this equation. Let's combine these two logarithms using logarithm properties. This will be logarithm of 80 over 20. This equals 100c. So this reduces to 8 by 2 is 4. So this reduces to natural logarithm of 4 equals 100c, or otherwise c equals 1 by 100 times natural logarithm of absolute value of 4. Now we can plug in this value of c into the previous equation. So let's consider this equation and plug it over here. In fact, we can also simplify this. So I'm going to use this. These two logarithms can be combined single. So we can write this as a single logarithm as a natural logarithm of p over 100 minus p, this absolute value, and this equals, I have combined these two logarithms using the logarithm properties. On the right side, we have 10t plus 100c. So we write 10t plus 100 times of c. C is 1 by 100 natural logarithm of 4. So this equals, these two will get cancelled. Here we get 10t plus natural logarithm of 4. This on the side we have natural logarithm of p over 100 minus p. Now let's take exponential on the both sides. We are going to exponential on the both sides. We raise both sides to the power of e. So this is also to the raise to the power of e. So this e and natural logarithm gets cancelled, and we get p over 100 minus p, and this equals e raised to the power of 10t plus natural logarithm of 4. Now we can simplify this right side expression. This basically equals e power 10t times e power natural logarithm of 4. Using the exponent clause, we write this sum of the power as a product of these powers like this. Now we see that this e and natural logarithm gets cancelled, and we are left with only 4. So we are going to get 4e raised to the power of 10t, and on the left side we have p over 100 minus p. Now we multiply both sides by this one. Basically we have to solve for p from this equation. So let's multiply both sides this one. So p equals 100 minus p times 4e power 10t, and this equals, we can distribute this into the terms inside the bracket. So this will be 400 e power 10t minus 4p e power 10t. Now let's add this to the both sides. And so on the left side we will have 4 plus 4p e power 10t. This equals 400 e power 10t. We factor p from the left side expression, and this reduces to 1 plus e power 10t. This equals 400 e power 10t. Now we solve for p by dividing by this expression. So we get p equals 400 e power 10t, and this is over 1 plus e power 10t. Okay, this one is actually 4 e power 10t, because when we factor p from these two terms, here we will be left with 4 e power 10t. So I'm going to change this to 1 plus 4 e power 10t. And so this is the final expression for the population of deer. Now using this expression, we are going to describe the behavior of population of deer. So this means we have to take the limit when t approaches infinity. So we take the limit of the population function p when t approaches infinity, and so this equals limit. We substitute the value expression for p, which is 400 e power 10t divided by 1 plus 4 e power 10t, and t approaches infinity. Now let's see how to solve this limit. Here we can factor this e power 10t. So this basically reduces to, I'm going to write down the numerator as it is, that is e power 10t divided by, I factor this e power 10t in the denominator, and when I do that I get 1 over e power 10t plus 4. Now we see that we can cancel these two terms, e power 10t and this e power 10t, they get cancelled out. And so we get, I can write down here, this equals limit of 400 over 1 by e power 10t plus 4. We let t approaches infinity. And when t approaches infinity, this approaches infinity, and 1 over infinity is 0, so this becomes 0. And so we will have 400 over 4. This equals 100. So we are able to determine that when t approaches infinity, the population approaches 100. The population of a deer approaches 100 when t approaches infinity. This means we can go back to the answer choices, and the population will approach 100 deer as t approaches infinity. So this one is the correct answer to this question.